Alright, so we're starting again. We're trying to finish nearest neighbor today. A couple of administrative notes. So your homework 0 has been graded. You should already have it available on Scholar. A couple of you are on the border. Come talk to me. I've already sent you emails. We'll pass out the solutions next time. Homework 1 is out today. It's due in roughly 2 weeks. It's due on Sunday night. Not exactly 2 weeks because I'd like you to finish the homework and come to class. I highly recommend that you start early. Continuing my intimidation tour. Here's what the homework looks like. Starts off with a couple of theory questions. Notice that it's 6 pages. This you should already be able to answer. This is stuff that we'll get to in the next class. Speeding up nearest neighbor stuff. This is theoretical portions that you should already be able to get to. And for theory, yes. So here is what you're implementing, and this is what a typical homework is going to look like. There will be 2 or 3 or 4 theory questions that will be related to what you're implementing. And then there'll be finally an implementation question. So you're implementing, you're performing what is known as cross-validation, which you'll learn about next class or so. But you're basically writing wrappers around nearest neighbor. So the problem that you're tackling is scene classification. So yes. So this is the page from last year. The one from this year seems to be dead right now. I'll go back and take a look. What you're doing is you're given a data set. You're given a data set of images. These are 8 categories: some coast images, some forest images, some beach images. I don't think there's a beach yet. We haven't overlapped with the coast. There's a highway, there's an inside city, so pictures like this. And so it's an 8-class classification problem. The input is the image, the output is one of the category labels. What you're spending most of your time in this is on nearest neighbor. So what we've done to make things easy for you is we've sort of abstracted away the computer vision aspects of this problem. So we've already handed you for each image a particular descriptor that is called the gist descriptor, just to show you what that looks like. So you'll be handed a MAT file. It contains training data, pre-separated out training and test data set. This is for each. So what GIST consists of is for an input image, what it tries to do is divide it. This is a descriptor for the entire image. It tries to divide it into a few cells, takes a couple of oriented 2-dimensional filters, convolves it, and you're looking at a few different responses at each of the pixel locations. The important thing it's not important what that descriptor is, because as far as you're concerned, the feature extraction problem has been solved for you. Data has already been given to you. You're asked to compute nearest neighbor. You can treat this as a vector in a 512-dimensional space. And here's what that vector looks like. This is what data looks like to you. There's on the x-axis is the number of dimensions, 512. On the y-axis the value. This is one image to you in this space. Just to show you that this space is somewhat reasonable. Here's another image, red and green overlaid right on top of each other. They're both from the same category, so they're both sort of, I think in case, coast images. And you can see that there's a lot of similarities, right? The responses are, they tend to fire at the same coordinates, they tend to drop at the same coordinate. And to put that in comparison, here's another image from a different category. So now it becomes a lot clearer. The green and the blue, image 1 and 2 are from one category. The green and the red are from one category. The blue is from a different category, right? So you can see that there's a clear difference in. So these are points in 512 dimensional spaces, and they're different. So when you compute distance from the green to the red, the distance will be small. When you compute the distance to the blue, the distance will be large. And so you'll be able to pull together neighbors of the same category. Okay. So things will make sense. What you're asked to do as part of the homework, we've given you, you're asked to essentially implement this is essentially a trivial function, right? It takes in some training data. You're given the labels for the training data in the data that we're giving you. The test data does not have labels, and you're asked to make predictions, right? So you're just computing the nearest neighbors, finally doing majority work. And you have to play around with how many neighbors that you're going to choose. And then you're going to implement something called cross-validation. So you'll actually take your training data and you'll split it into folds. And it's described in the document, and we will cover it in the coming classes as well. Okay? And finally, there's an extra credit portion in which you will actually upload your entries. So this is every single time. Okay, so this is it from last year. Chin was the TA last year as well, so that's her entry, and this is the leaderboard for everybody else uploading their entry. So you don't get to see how you're performing on the test data until you upload on this ladder, and that's me performing at chance. So if you upload a random number generator, that's what you get. So beating me is not hard, but if you're not beating that, then there's a bug in your code, which is great. That's fixable. I think Kaggle allows you 2 uploads per day. It's actually preventing you from overfitting to the ladder. So plan this out. You will not have too many submissions available. So if you're trying to do this on the last day, you just have 2 uploads. That's it. Let's see, and it's going to show you. So there's going to be a public leaderboard and a private leaderboard. 30% of the test data will be used to compute a public leaderboard. You'll be able to see that as soon as the competition is open. 70% of the test data will be held out for the private leaderboard that we will have access to, and we will release once the due date has passed. Yeah. So what this homework is trying to get you to do is to basically establish your infrastructure. There isn't much to code in terms of nearest neighbor. It's just distance matrix computation and sorting. But it's trying to get you to sort of think in terms of train, test, validation. There's a parameter, how many neighbors to choose, and just sort of getting your code base and infrastructure set up for these kinds of problems. Okay. One thing that we specify is that you can't use any external machine learning or nearest neighbor libraries. If we're asking you to implement nearest neighbor, please do not use MATLAB, KNN search, or KNN predict. That defeats the very point. Okay? You're implementing everything yourself. In general, the use of linear algebra libraries is okay. So later on, SVD and eigen decomposition stuff, you're not going to ever implement. But in general, when we ask you to implement a machine learning algorithm, we will not allow you to use external libraries. For the extra credit, however, feel free to go crazy. You can use whatever you want. It has to be a nearest neighbor submission. You cannot, for example, if you go to the web page of the dataset, it says the best performing method is an SVM. Can't use an SVM. Okay? So it has to be a nearest neighbor classifier, but you're allowed to do anything. You're allowed to do feature selection. You're allowed to pick K. You're allowed to, combine features, whatever. Use weighted KNNs. Go crazy. Okay. Any questions about the homework? Not yet. Good call. Okay. It's one just sort of pedagogical note. I would strongly suggest When you walk out of here, find a few people, make a team, just get a study group together. A lot of these questions are going to take time. Sometimes you'll miss certain subtlety. We encourage you to, this is not homework zero, we encourage you to sort of get together and think about things together, write your own and code your own solutions. But other than that, it's a lot easier if you team up with 3 or 4 people, sit down, make an appointment, actually get started. All right. So that's that. Okay. Good luck. Yes.
It looks like they're not available the grades for the homework here.
They're all pass. If you're on, it's only pass or you're on the borderline, and the people who are on the borderline have been ignored. Okay. All right. So here's where we were last time. So we were looking at nearest neighbors, and hopefully now that picture makes a lot more sense. It's a Voronoi diagram. We sort of told you that this is the sort of broad format of any nearest neighbor algorithm. You answer these 4 questions and you've specified yourself a sort of instance-based learning algorithm. What this algorithm does is it maintains a data set, the training data set, keeps it in memory. You have to say, what distance metric am I searching for? How many neighbors do I find? Do I use a weighting function? And how do I make the fit once I get my neighbors? And so one nearest neighbor was just use standard Euclidean distance. There is no weighting required, just predict the same output as the nearest neighbor. Right? It's the simplest sort of algorithm. And we had looked at it for classification and regression. Right? This is simple one nearest neighbor for function fitting. You would call this interpolation, nearest neighbor interpolation for this. Okay? We'd also looked at one way, the idea of nearest neighbor for classification and the kinds of distances you use. So we talked about this is the boundary. Every point in this cell has the nearest neighbor x, and therefore whatever the label of x is, that gets propagated to this entire region. Right? And it matters how you compute distances, because if you start scaling your dimensions, these sort of cells get shifted. We had introduced you to a couple of distance metrics, the Manalobis metric, where you're sticking in a positive semi-definite matrix in between the differences, and what it does is it'll sort of change the contour maps from circle to ellipses or non-axis aligned ellipses. We'd also introduced Minkowski's distances, which were LP norms, if you will, and they, L1 and then infinity were the special cases. They were essentially more angular. You meet them again. You meet especially L1 again if you ever study sparsity, and we don't get to that. Okay. So here's what we're trying to get to today. We're trying to finish this particular topic that we had started, which was weighted or kernel classification, and we're trying to argue why nearest neighbor shouldn't work. It seems to work really well, but we'll try to argue why it should fail. There should be no reason, especially in the kind of data that we're handing you for the homework, it just shouldn't work. And we'll argue that it's this concept of course definition. Okay, so let's get started on the first one, the weighted case. So we had made this argument that all neighbors are not the same. It would be nice if I could weigh my neighbors based on how much I should trust a neighbor. Okay? And one of the reasons we tried arguing that is because regression with one nearest neighbor tends to overfit pretty badly, and we'll sort of, it tends to be extremely bumpy. Here's a point, it sticks to that, when it jumps a little, there's no smoothness in this function. If there's ever sort of an outlier, if you will, it's unclear, we haven't defined what an outlier is, but it tends to fit every single point, and it's extremely bumpy, if you will. And somehow, increasing K sort of does a better job, but not quite. You don't quite fix that because you're still carving out this odd sort of bumpy decision boundary. Because at some point, the neighbors will flip, and so you still see these corners happening. These jumps will keep happening because you're essentially doing your division by 9, right? There's not that much going to be smoothness. So we had talked about something called kernel classification. We haven't actually defined what a kernel is, and we will leave that out for another lecture, which is going to be on SVMs. But for now, we will just talk about weighted regression or classification. Can we assign a weight to every neighbor that we get? And that's, it's going to be a different answer to these questions. And the answer to the distance metric is, okay, let's take Euclidean for now. Let's make our life easy. You could change it to other distances. How many neighbors do I look at? All of them. I'm going to look at every single neighbor in the training data set. And what I'm going to do is I'm going to assign a weight, Wi, which is, it's going to be some weight. Right now I'm showing you a Gaussian form. It's negative of distance of the query point to this training data point I divided by some parameter that we'll call bandwidth parameter or kernel parameter, right? And this is the weight of training data point I for this query point. Right? Different query points will place different weights. Why? Because this distance will change. Okay? And what this will try to do, and we'll draw this on the board, it will try to weigh nearby points stronger. And then once you've assigned, given your test point, I've assigned a weight to every single training point. Now, how do I predict? I'll just do a weighted regression or weighted majority. Okay? So far, so good? So the outline of the algorithm was done last time. Why, WHY, why this sort of function? You can use some other sort of curves as well. You can use sort of, for example, 1 over d type relation, 1 over d squared. You can use a couple of different weightings, right? The general message is what you'd like to happen is as the distance increases from the test point to the training point, that this is a decaying curve, right? It's the general sort of idea. I trust neighbors that are close to me, I don't trust neighbors that are far away. And one thing that we were trying to answer last time is the effect of the, kernel width or the bandwidth parameter. And let's look at that. So we'll answer two extreme questions. One is what happens as the bandwidth goes to infinity, what happens as it goes to 0. Okay? So let's answer that question. This is what that function sort of looks like. This is x test, right? And this is sort of weight of a data point x. So as the distance increases, as you go away from x test, d of x test over x I. Weight of I. So as the distance increases, when you're close by, you have high weight, it goes to 0, it decays. Okay? And the equation we wrote down was Wi to the negative distance squared xi. I've dropped x test for brevity, and this is whatever. So I is the training data point, and x is the query point, xi is the training. Okay. The first part is really easy. Let's try to analyze what does it mean? Your bandwidth is going to infinity. I'm sorry?
The exponent goes to 0 and then
the exponent goes to 0, right? So your denominator is going to infinity, this ratio is going to 0.
it's going to be 1.
Yeah, so this is approaching 1, right? So the limit is 1. And our prediction rule for regression was y hat is equal to summation of wi, yi, 1 through n, summation of wi. If everybody is weighted equally, then in the regression case, you're just predicting the data set mean, right? Mean of the data set. So you're just predicting the average value. Doesn't matter what the input is, you're always going to predict the average value. And for classification, you're just looking at the distribution of classes in your training data. Right? If one class just exists more time, if you have 100 samples from one class, 99 from the other, you're always going to predict one with 100 samples. It's always going to win out. Okay, that part's easy. How about the other part? Your bandwidth is converging to 0.
0 weight to all the points except the nearest point.
0 weight to all the points except the nearest point.
means, no, it will be some weight for the point which has no distance from the destination.
Yeah, so, but what if that, so let's assume distances are always positive, so I never query you on the training data. Yeah, so the intuition that you're trying to get to is correct. You're essentially looking at this. Okay, sigma is going to 0. Basically, it's this thing is converging to a delta thing. The ratio is going to a really large number. There's a negative sign, so e to the negative of a really large number. This is converging to 0. Okay, that's fine. But then this is a problem, because if the weight starts converging to 0, then the numerator is 0 and the denominator is 0. You haven't really defined the limit here. You can't really predict. Okay, but we can, the intuition there was completely accurate. We can just a little bit of careful analysis, and you can see what this is going to be. So let me actually just write this down. For the regression case, and classification is going to be extremely similar. Let's say this is I1 through n, e to the negative, by being consistent, yes, distance squared, x comma xi, divided by sigma squared, summation 1 to n, e to the negative, yi here, okay, so far nothing. I haven't done anything. Just written the definition out. Here's the trick, which essentially formalizes the intuition that she was trying to get to. That somehow weights are going to 0 everywhere. That as this is approaching 0, the weight is approaching to 0 everywhere, but not at the same rate. Some places it's approaching to 0 faster. And so what you do is, here's a particular trick to keep in mind. Let's go ahead and multiply by the distance squared of x with xj, a special point xj, where j is the index of the nearest neighbor, of the one nearest neighbor. Okay, people at the extreme. Can you not work on your laptop, please? Sure. So j is the index of the one nearest neighbor, and what I'm going to say is that this is essentially the odd min over I 1 through n of the distance of x to xi. Okay, so just the one nearest neighbor. What we're going to do is we're going to multiply and divide by the one nearest neighbor. X over xj. Squared by sigma squared. Any idea why we're doing that? Why are we multiplying by and dividing by the exponent of the distance, so the one nearest neighbor? Any guesses?
That's the smallest.
At the nearest neighbor, the weight won't be 0. It's going to be.
Very nice. At the nearest neighbor, the weight won't be 0. I'll shift to the center so everybody can see. Basically, what's going to happen is you're adding a particular quantity. Here we're summing over everything. At the nearest neighbor, it will cancel out, and everywhere else, it will still continue to go to 0. And we've made a simple assumption that there is a unique one nearest neighbor. Right? If there are multiple one nearest neighbors, then it will cancel out in multiple places. We're keeping our analysis simple. Right, so this is simple summation I not equal to j, so everywhere other than j, we have exponent of distance squared x comma xi minus, there's a minus here, minus x comma xj divided by sigma squared. Times yi plus e to the 0 times yj, and the same thing here. Summation of i1 j e to the negative distance to xi Okay. What I'm essentially doing is by multiplying and dividing by the exponent of the distance to the nearest neighbor, it cancels out the negative distance here for the nearest neighbor. That gives me a term e to the 0, the weight of 1 for the nearest neighbor. Everywhere else, it does exactly what I want it to do. Everywhere else, it's the distance of anything farther than the one nearest neighbor minus the distance to the nearest neighbor. So this quantity is always positive, right? Because we took the distance which was the smallest, so this numerator is always positive, and now everything's fine. There's a positive, negative sign sitting there, sigma is going to 0, so far so good, right? Sigma going to 0, this is a large negative number, this weight can now safely approach to 0, no problem. The denominator is 1, the numerator is yj, right? This is the only thing that gets left behind. Right? So the answer is simply sort of yj in this case. So the predictions that you would have made with the one nearest neighbor. So if you think about this curve, sigma increasing is sort of putting a weight of, as sigma goes to infinity, you're putting a weight of 1 everywhere. Right? And that's doing a data set average. As sigma is going to 0, you're putting a weight of, it's difficult to, I can't precisely draw it here, but it's going to a delta function where the delta is happening because of this careful analysis at the one nearest neighbor. Right? So you're just listening to your one nearest neighbor, everybody else the weight is 0. Right? Does that make sense? And so you're sort of smoothly interpolating between the one nearest neighbor and the data set average. We know the one nearest neighbor is jumpy, the data set average is just constant, and in between that is fine. So here's what that looks like. So this is x, this is y, those are the points given to you. This is a small bandwidth parameter that's increasing to a large bandwidth parameter. What's happening is when it's small, it's trying to make sure it is essentially a step function, right? If you remember this slide, if you remember this slide, the one nearest neighbor has to pass through all of these points, right? Because when you query that point, the distance is 0, so it has to give you back that same answer. So it has to pass through all of these points. When it's small sigma, not exactly 0, it's going to try and get close to all those points, because when it's extremely small, you're putting a lot of weight on the one nearest neighbor prediction. So you try to get extremely close to them, but it still somewhat smoothly interpolates to be. As it becomes larger and larger, you're essentially converging to this line, which is the data set average. Right? You're looking at the y values of every single point, and no matter what the x value is, you converge to the data set average. Does that make sense? Okay. And so, this is all illustrated for regression, but you could apply the same idea to classification. Right? You could look at your neighbors, weigh them based on distances, then do majority weight, and then do prediction. All right. So let's look at this. So now that we've looked at a few of these things, let's look at what are the problems with instance-based learning. It seems extremely simple. It seems extremely attractive. There's not much to do. It's really easy to implement. We can compute distances. Why are we done? Why are there so many of these other machine learning techniques? Here's a few of those problems. It's extremely expensive, for one. There's no real, remember we split it out into a training stage and a testing stage. The training or the learning stage isn't really doing anything. It's just memorizing, right? So there's no work done in training. All of the work has been relegated to testing. So it's extremely expensive at test time, because if you have 1 million data points, then for every single prediction that I have to make, I have to go query through this data set to find the distances to 1 million points to tell you what the nearest neighbor is. Right? And therefore, a lot of the work done in this area will be on approximate nearest neighbor search. A lot of times, it doesn't really matter whether we get exact nearest neighbors. If you have enough data and they're densely sampled, often approximate neighbors, so algorithms that give you neighbors that are guaranteed to be within some epsilon handle. Right? And in fact, that's something that you're looking at in the theory questions of your homework. You try to look at how can we speed up distance computations by proving some bounds to a particular point. Here's another problem that might happen. It doesn't really work well when there are a large number of irrelevant features. Often what happens is you're not quite sure what to measure. So you go overboard and you measure 10,000 different things. So if I want to predict housing prices, let me find out how many people were living in that house, let me find out what the schooling district was, but let me also go ahead and measure the temperature of the day and a bunch of things that I don't believe to be related to the quantity that I'm trying to predict, but I'm just trying to be safe. Let me just measure a lot of things. If you do that, you're stacking together a vector that has a whole bunch of entries that don't indicate anything about the category that you're interested in, right? And so then when you start computing distances, they're overwhelmed by the noisy features. Does that make sense? And so often what you're going to need are sort of dimensionality reduction techniques or feature selection techniques. Can you throw away some features and keep only a subset? All right, the third problem that happens a lot, okay, we'll see the proof in this lecture actually, is something that, it's a very strong word, but is known as the curse of dimensionality. Perhaps a little theatrical, but that's what the name is. The intuition behind that phrase is that as you go to high dimensions, distance computation essentially becomes meaningless unless you make some assumptions. Okay? And I'll give you a couple of examples today that will try to illustrate this idea that somehow distances shouldn't mean anything when you go to 500 dimensional spaces, for example, as you're doing in your homework. Okay? So let's look at that. Are there any questions about this? Anybody see any other problems with nearest neighbors, or if you've tried nearest neighbor in past somewhere else it may have failed?
Like, can we just implement some form of learning by when you have new test data and you predict which class you'd like and then make it as if it's a training data?
So you're suggesting something known as bootstrapping or self-taught learning. His question was, can we make a prediction on a test data point and then assume that our prediction was correct and treat that as a training data and just bootstrap from there? Yeah, so that's a subfield. So just like we said, there was supervised learning, there was unsupervised learning. The kind of problem that you're calling a self-taught learning, where exactly as you said, you make predictions, assume they're correct. One of the major problems that happens is of something that is known as concept drift. Over time, your predictions tend to be inaccurate, and then you assume that they're correct. Now you have more data, but the incorrect thing is now being called correct, and over time, what you end up learning is not quite the concept that you were interested in. But that has nothing to do with nearest neighbor, for example, that would happen with any machine learning.
The
Yes.
regression slide that you showed, that bumpy function.
Yeah.
So how do you would it be possible to was it possible that there was another regression function? So I will be fitting to those points, but if I were going like this, instead of going this way long, I would have jumped before. Is that the only possible solution, or there are many solutions possible for fitting that point?
For fitting this function?
Yeah.
No, this is exact, right? So what's happening is that this is your x-axis, and if you're doing one nearest neighbor, at every point you know exactly it is determined who your neighbor is, right? It's going to be this point, and on a one-dimensional plane, essentially you're chopping off thresholds,
Yeah.
right? When you're left of the threshold, this guy will be nearer to you. When you're right of the threshold, that guy will be nearer to you. And in between those thresholds, it will be a horizontal line, because if you look at the equation, it just says y hat is equal to y of one nearest neighbor, right? So it's a constant line in that thing. And in fact, if you try to go to higher dimensions, it's this Voronoi cell is the thing to keep in mind, right? This is 2 dimensions, but you can think of higher dimensions as well. You're essentially breaking up your feature space into a bunch of these cells. And on these cells, if you do one nearest neighbor, you're only going to make a single prediction, right? So it's a piecewise, constant sort of a function that you're fitting to this data set.
And also boundaries are lying in the perpendicular bisectors of the nearest point.
Right, so you can, on this 2D, for example, these are perpendicular bisectors. Yes?
Because dimensionality, isn't it that all the features have to be normalized
let's look at that. So let's look at the assumptions in that. Okay. Any other questions about this? Yes.
I was wondering on the example where you're doing regression,
Yeah.
it looked like at the ends it was always, it was actually a different slide where you were doing the weighting
Yeah.
of them. Like at the ends of it, it was always, at the upper end it was underestimating. And like, is there any way to fix that problem? Like when you have a very narrow bandwidth, it's not as much of a problem, but at the ends it's like it.
So at the ends, you will run into a problem, right? Because if you think about this is a one-dimensional space. You go a little bit away from this. There's one nearest neighbor, and if your bandwidth parameter is small, you're putting most of the weight on that point. So you're essentially sort of flattening out to that one point, and it continues from there. It doesn't happen here, but now you're essentially sort of you're being pulled to the data set mean, if you will. And by the way, this is just all about nearest neighbor and sort of weighted nearest neighbor, right? In the next few classes, we'll look at model-based fitting. So we'll look at linear fits and quadratic fits and polynomial fits to regression, and they'll be far more powerful than just this nearest neighbor. Yes.
So pretty much for when you coefficient sigma that
Bandwidth sigma, yeah.
when it approaches 1. So if you have like let's say 5 points and then another point here.
Do you really mean one, or like are we talking about the weight or the sigma?
I'm talking about the one, yeah.
So this is when sigma is going to infinity.
Yeah, I'm talking about
Okay.
when sigma goes higher. So when you have like 5 points and then you have a point in the middle somewhere, and then when sigma is higher, and then you choose a point that is right next to that point, it might give you the category of those 5 points instead of the one.
These figures are about regression, right? We're not doing classification or categorization. This is just about one-dimensional y fitting that function. Right? So this is about regression. In terms of like, if I'm thinking classification, then what was your question there?
Yeah, then I'm talking if you have like 4 points that are in the same category,
Yeah.
And they're around one single point.
Yeah.
And then you choose a point that is like a little next to that point. And then with when sigma goes high,
Yeah.
then it might give you the category of those 4 points. And then when sigma goes lower and lower, it will give you more and more the point that is next to it.
Right.
So like when you choose sigma, it could give you
Different predictions. Yes.
predictions.
That is completely correct. Yes. So we know that at infinity it's going to give you just the most frequent class, and at 0 it's going to give you the one nearest neighbor class. So somewhere in between it has to switch, and it may switch at some different value. And this is, for example, a parameter or a hyperparameter. These are called hyperparameters of your approach, and you'll have to fit these from data. And we'll talk about that also next. Yes.
Is there a way to find like the optimal kernel width, or is it just kind of you do it, you test it once?
No, so there are ways. So for example, in this case, you could, that's a continuous valued sigma, so you would sort of define an objective function which has to be smooth in sigma, and you sort of minimize the loss. Yes, there are ways to do that. Once you start going to classification, then the loss function you care about is misclassification rate, right? Whether you predicted the correct thing, that's not going to be differentiable in sigma. At some point, when sigma is small, you may be predicting the correct thing. When sigma goes large, you may predict an incorrect thing, and there's a non-differentiability there, and so you won't be able to find, at least with continuous optimization techniques. That's good. Yes. Okay. I think there's been enough debate. I feel like we can continue. All right, I'll take another one.
So, by varying sigma square, they're actually kind of limiting the distance in which we'll raise the neighbors, and by limiting k, we're also limiting them. So I think how do we tune it? If the data set is sparse, very sparse, then maybe the kernel function doesn't actually matter. So between two, it wouldn't matter because it will always be 0. So how would you?
So if you look at, there are several parts to that question. So the question was, the value k, the number of nearest neighbors, seem to also be telling us how many neighbors we want to consider. Sigma also tensor doing that, what's going on? So one thing you can think of is there is another type of kernel that you can use that is, assigns a constant weight as long as you're within a particular distance range, and then drops to 0, right? This kernel essentially corresponds to k nearest neighbor, right? Yeah, this is specifying after some distance, I no longer listen to my neighbors. So for every data point, it's listening to a different number of neighbors, right? So basically what's happening with a bunch of these functions is that you are smoothing out, k can be an extremely jumpy thing. You have to go 1, 2, 3, 4. With sigma, you're sort of smoothing out, you're listening to every single neighbor, but the weights are going to 0, so you're not going to, won't matter. Computationally, it's going to be a problem because now suddenly you have to assign a weight, and even though that weight is 0, you have to sort of compute that weight and then find neighbors. So often people will look at functions that are like this, or they will threshold some smooth decay function. So they'll take a function that is smoothly decaying and they'll threshold at some point. So if the weight is less than some threshold, then I won't actually compute, then I won't actually find it 90 seconds, because that will make things faster. Okay. If you want to stand up and stretch, now is your moment, but let's keep going. All right. Okay, so what I want to do is I want to give you an intuition for cursor dimensionality, why things should become, basically it'll be two short sort of derivations, they'll be extremely short, but the point will be why things should be hard in high dimensions, that we're sort of making, when we look at these pictures, we're looking at one-dimensional spaces, two-dimensional spaces, and things should become, they act differently in high-dimensional spaces. So here's example one. Here's the thing that I'd like to consider. Think about a sphere of radius 1, okay, centered at the origin. So far so good, nothing too problematic. Consider an outer epsilon shell of that sphere, and I'm going to ask about the ratio of the volume of the shell to the volume of the sphere, okay? And this will tell us something about, what we expect in high-dimensional spaces. So let's do that. All right, so let's see. So here was the question, right? There's some sphere. It's centered at origin. It's in some dimensional space. This is of radius 1, and what I want to consider is a shell that lies on the inside. The thickness of the shell is epsilon, so that radius is 1 minus epsilon.
Inside or out?
Inside. But
Doesn't matter.
It won't matter all that. Okay. So let's walk through our intuitions. One-dimensional space. What's the sphere in one-dimensional space? It's just a line. Here's origin. Here's radius r plus r minus r. What is the volume of a sphere in one-dimensional space? So it's just a line. So we're just asking for length, right? So it's just 2r. Let's look at a sphere in a two-dimensional space. That's just a circle. This is just pi r squared, right? His volume is just area in this two-dimensional space. You go in a three-dimensional space, like crappy drawing. You go 4 by 3 pi r cubed. And at this point, I will appeal to something called proof by ellipsis. There's a pattern here, and that pattern is some constant which depends on dimensionality times r to the dimensionality. If you're a mathematician, you've heard of something called mathematical induction. I call it proof by ellipsis. Okay, so you can prove that this is, the volume of a sphere in d-dimensional space. And the quantity we're interested in is the volume of the shell divided by the volume of the sphere. Okay, let's actually raise this. I want to stay in the center. So here's volume of shell in volume of sphere. Okay, volume of shell, well, I can just look at the, k times r to the d. I can look at the volume of the sphere minus k times let's make this simple, right? It had radius 1. So 1 minus epsilon to the d. Even better. And the denominator was again k times 1 to the d. So far, so good. So this is 1 minus epsilon to the d. That's what the ratio is. Okay? Now think about what's happening to that ratio as d becomes larger. So you're collecting more and more information about each sample, right? I will argue as d goes to infinity, but really I'll show you a plot where things kick in at 10. It won't be infinity, right? It'll kick in very quickly. So what is happening here as d goes to infinity? You have a number.
Approach 0.
What?
Is approach 0.
This is going to 0, right? This is a number less than 1. It has an exponent that's going to infinity. So this is going to 0. So the ratio is approaching 1. Okay? The ratio of the volume of the sphere, of the shell to the sphere, which means most of the mass is lying at the extremes. Right? If you're a data point and data has been sampled uniformly in this d-dimensional space, most of your neighbors are lying here. Does that ring in? If you're in a d-dimensional space and I uniformly sample data in a d-dimensional space, and you're a test point, most of your test point are, most of your neighbors are lying here in that shell. Why? Because we just argued that most of the mass lies in the shell, and volume is, if you're sampling, then it's going to be proportional to the volume. So as dimensionality increases, as you measure more and more things about your data, everything becomes farther and farther away at the same distance. Everything becomes at this outer shell. So your neighbors are going away.
So how did you go from that equal to 1 to our data is on the shell or mass?
So
the ratio is 1, but what do those represent?
So the volume of the shell is most of the volume, or nearly all of the volume of the sphere.
Which is all your points.
And let's say the points are being generated by uniform sampling in this. So let's say if I sample uniformly in the space, then how many points I get in a region is proportional to its volume. Does that make sense? So think of a uniform distribution in one dimension, right? It's between some points L and U. It's a uniform distribution. This is what the density function looks like. And if you ask me the question, how many points are expected to fall within this interval, it's the length of that interval. Right? So the longer the interval, the more points are expected to fall in that.
Okay.
That's why you go to d-dimensional space, it's the volume. In the sphere's case, most of the volume is sitting out at the outer shell. Therefore, when you sample points, most of the neighbors are sitting out into the shell. Right? That makes sense? And it feels like a tricky argument. It feels like I'm sort of cheating, that this should happen at infinity. It doesn't happen at infinity. On the x-axis here is that epsilon quantity that we were talking about, the size of the shell, the radius difference. On the y-axis is the volume fraction, so the fraction that we were talking about. Dimension 1, so far so good, straight line. Right? This is where our intuition comes from, the straight line. As epsilon becomes larger, more and more volume exists in that shell, right? But this is what it actually looks like in 20-dimensional space. Epsilon has to become extremely small, it has to just grow from 0 to 0.1, and suddenly most of the volume lies, nearly the volume lies at the extremes, right? Notice I appeal to infinity, but this plot is only with 20. So if you measure 20 things about your data, then if your data is uniformly sampled in a 20-dimensional space, then all your neighbors are lying at the outer extreme of a sphere center by each test point. And we're going to 512-dimensional spaces, right, in the whole book. So that's one problem. Anybody catch what can be your way out? So, any flaw in my argument? Yes?
7 is not uniform.
Data is not sampled uniformly. Excellent. If there's a logical conclusion, can't argue with the logic, argue with assumptions, right? So I assume that data was sampled uniformly. Data doesn't have to be sampled uniformly. I'm giving you images in the homework which live in a 512 dimensional space, but they don't occupy a 512 dimensional space uniformly. If they did, nearest neighbor would be extremely common. Okay. I have some. Was there a question?
Yeah, so if it was a line, how would you sample data not uniformly?
Not uniformly? So on a...
If it wasn't just one dimension.
Sure. So on... Let me... Here's a line, this is the origin, this is what a uniform distribution looks like in the sense that I give you a cutoff point, L and U. If you're not comfortable with density functions, think of these as bins of a histogram. And as you have infinite data, the histogram becomes nearly flat over the bins, right? Mm-hmm. It means that the probability of falling into any of those bins is nearly the same. A non-uniform density function, for example, you're already familiar with it. It's called a Gaussian, right? It's non-uniform in the sense that you know that data is most likely to be around the mean in this case.
Okay.
In a high-dimensional space, 2 or 3 or n, we're sort of hoping that it's not that the data occupies this entire space uniformly. It's not that the how do I draw this? Yes, it's not like a cube that is your distribution, that there is some sort of underlying subspace, for instance, that most data comes from this subspace, that they all lie on this plane, for example. They're not going to all lie on a plane, but that's sort of one way to explain it. That even though they're living in a 512 dimensional space, the intrinsic dimension is lower. It's not uniformly over the 512 dimensional space.
Okay.
I didn't get what was the problem with data lying only in the cell, mostly lying in the cell.
The problem is going to be that most of your neighbors are far away from you. That all your neighbors lie in this cell, which means in an L2 sense, they all nearly are the same distance.
But if my test point is also in this cell, then...
But it's for any test point. The math didn't care about where that test point lied, right? So you give me any test point, this is not origin, this is X test. Any test point in a d-dimensional space, all the neighbors lie nearly the same distance. Does that make sense? Right. Okay. This is one of the intrinsic problems in dealing with sort of high-dimensional statistics or high-dimensional analysis. Our intuitions and all the pictures we draw come from low-dimensional spaces, and we have to reason about not high-dimensional. The only way to do that is sort of analysis and limits. Okay. All right. So let me look at, before I let you go, let me look at one other way of showing the same idea. I personally have found this extremely interesting, but let's see. Here is example 2 of the problems with high dimensions. Okay, so let's think about the distribution that he was trying to get us to think about, right? So let's think about the uniform distribution, or the Gaussian distribution on 1D. And I hate to go into this example into detail because we will do like a probability review and a couple of those things next lecture. So this is jumping at the gun a little bit because this example will use some things that I want to clarify next time. But I think it'll make sense if you've taken a basic sort of probability class. So you live in a, let's say this is X. This is one-dimensional space, and that's the distribution. right? Let's say you sample data according to this distribution, which means here's one point according to this distribution, so it lies here, and let's compute its distance to the origin. You sample another point, you compute its distance to the origin. You sample a third point, you compute its distance to the origin. You expect some distances to be small, because sometimes you'll sample close to 0. You expect some distances to be large, because sometimes you'll sample far away from 0. You expect there to be some variance. Some distances will be small, some distances will be large. I may change the distribution. If I sample according to a Gaussian, most points are close to 0. So most points have small distances, but every so often you'll see a point that is far away from 0 that has a larger distance. Okay, so far so good. So you expect some variability in distance. In fact, you can do this really easy. You open MATLAB, you sample random according to uniform. Just look at the distance to 0. Now let's do that in a d-dimensional space. Okay, the quantity that I'm interested in is x minus 0 L2 norm squared, where x lives in some d-dimensional space. Okay. And in order to normalize the effect of dimensionality, right? If you live in a 1,000-dimensional space, you just add on more things, right? Because this is basically summation of xi squared, right? So I going 1 through d. So you're just adding more numbers. And so what I want to do is I want to look at the average distance over the dimensionality, right? That way the numbers are comparable. That makes sense? So if you're in 1-dimensional space, I'm dividing by 1. If you're in 2-dimensional space, I'm dividing by 2. All right, and here comes the crucial assumption, and this is hint, this is what you should challenge later on. The assumption is going to be, let's say xi independent of xj, each dimension, and they're all sort of, xi is distributed, let's say Gaussian, with mean 0 and variance lambda squared. IID, each of your dimensionality is IID. Right? This is uniform, I drew the Gaussian, each dimensionality is Gaussian. All right, and I'm interested in this value right here, the average distance of a point to the 0. Is this beginning to remind anyone of something? We're looking at a summation of random variables that are all IID.
Tends to uniform.
Tends to uniform.
If you sample n.
Should it really tend to uniform? So there is a tending to something theorem. Normal, something called central limit theorem. If you add enough random variables together that are all independent, identically distributed, the sum of those random variables, or in this case, the mean of those random variables, goes to a Gaussian, a normal distribution. Central limit theorem, for those who have forgotten, is if you have zi, a random variable, and all the zi's are IID, with expected value of zi, let's say mu, and the variance of zi, let's say sigma squared, 1 over n summation of zi goes to a normal mean mu and variance sigma squared by n. Okay. So this is looking just like that, except zi is xi squared. Right? This is becoming a Gaussian with mean expected value of xi squared and variance of xi squared divided by d. Doesn't really matter what those numbers are. Doesn't really matter what expected value of xi squared is. You can compute it, right? You just crunch through the math. You guys have already done it in homework 0. I gave you an identity proof that variance is equal to expected value of xi squared minus something, right? You've done it. Doesn't really matter what those numbers are. The distance, the average distance in the dimensionality is becoming a Gaussian. But more importantly, the variance has a 1 over d factor in it. So as d tends to infinity, what happens? Variance is 0. As you go to higher dimensions, when you calculate distances, they become nearly constant, right? Because the variances are becoming 0. When you look at a Gaussian, a variance is telling you the estimate of the spread of the Gaussian, right? The variance is becoming 0, so you're essentially, your average distances start looking like this. It's only one distance. Everything is equidistant apart, and it's the same distance. How can you possibly do nearest neighbor if the entire data set is the same distance apart? So, what's the problem?
Uniform distribution.
Oh, there was no uniform distribution here.
All the distributions are same across every dimension. Identical distribution.
Identical, okay. What were you saying? Independent, actually that's the bigger problem. You can actually relax central limit theorem that the variables can have different distributions. That's the independent part. If you're really living in an infinite dimensional space with independent random variables, you cannot escape this fact. You are going to get to the same distances. It's the fact that when we're giving you this data which lives in 512 dimensional space, 1, 2, 3, it's not that they're actually independent. Those quantities that we're measuring are not independent. And thankfully that's the savior. When you really go out into the world and collect data, those different quantities that you're collecting are not independent. Sometimes it feels like a problem that we're collecting essentially the same information in multiple ways. That's not. If you were collecting orthogonal information in a sense, you would be hopeless. You would not be able to do learning essentially, right? So correlations in data help. That is essentially the reason why nearest neighbor methods are able to. Okay. All right. So at this point, we are done with the nearest neighbor module of the class. I'd like to specify. Here's what we expect you to know out of this. We'd like you to know that this is. We'd like to understand how to implement nearest neighbor, which you will in your homework. This is one of the simplest learning algorithms, and if you have a lot of data, this is one of the first things to try. It's often when your data is sparse and things are really far away that nearest neighbor might not make a lot of sense. But often it's very hard to beat this strawman approach. We didn't tell you how to pick k, or when you smooth it out with a weight, we didn't tell you how to pick sigma. It's, picking k is unfortunately discussed, not a continuous optimization problem. In your homework, what you're doing is you're picking k over something called a validation set. So you will go to held out data, which essentially means try it all. Try it all and see which ones work, and that's what you're going to pick. The important thing is going to be you don't try on the test data. In this case, we have made sure that you cannot try on test data. So you're going to partition the training data that we've given you into something called a training set and a validation set. We will cover cross-validation next time, but you're going to try different values of k on your validation set. You're going to try making predictions of k equals 1, 2, 3, 4, see which one works best, and that's what you will use on the test set. Okay. The idea of kernel, regression, or classification, often smoother than nearest neighbor, and we expect you to know things about the stuff that we taught you about, curse of dimensionality, irrelevant features, and the fact that the key problem in nearest neighbor is speeding it up to with approximate experience. We have also gone over this sort of the idea of loss functions, what classification and regression is. Training and test data, and we've sort of told you what a hypothesis class is, this idea of overfitting and generalization. These are concepts that we will meet over and over again. Sort of essentially, every time we cover a particular method, we'll tell you what the hypothesis class is, we'll tell you what overfitting in this context means, but we'd like you to keep these particular concepts in mind because you will see them over and over again. Okay? At some point, there will be like an in-class quiz. I'll actually announce it because I need people to bring their laptops in class, so it won't be it'll be like a quote-unquote surprise quiz because you won't be surprised. But but we'd like you to go over the reading, which is from the part of the book, and please start working on it. All right, let's stop there.